So last lecture we discussed formal power series, formal power series, and we so has the definition. We have we can sum and product, calculate the sum and product of the formal power series. We define the inversion. So if we have formal power series, we can try to calculate its inverse. And so now we have all we need to do some tricks. So first of all, let's start with discussing linear recurrence relations and how to solve them using formal power series technique. So we start with Fibonacci numbers. So if you have sequence, we can look at the corresponding generating function. So we have, if we have sequence A0, A1, etc., then we can look at generating function which is A0 plus A1x plus A2x squared, and so on. So here, generating function for the Fibonacci numbers will be the formal power series, which starts from A0, then F1, then F2, and so on. So we want to find, so if in our case F0 is 0, so we can write it as x plus x squared plus etc. And so we can just take the x out of the brackets and then try to calculate the inverse of this formal power series. Or in other ways, we want to find a short description of this infinite sum. And the trick is we can use the recurrence relation. So what's recurrence relation? How can we use it to define what this f(x) is? If you look, so if you want to use this identity, we need to have f2, f1, f0, f3, f1, f3, f2, f1 with the same power of x. And to do this, we can just multiply f of x by x and by x squared. So here we can find that x time f of x is f0 x plus f1 x squared plus etc. X squared time f of x is f0 x squared plus etc. And so if we look at the coefficients here, we'll have fn times xn here, fn minus 1 times x to the power n here, and fn minus 2 times x to power n here. And so if we subtract lower rows from the upper row, then this will vanish because fn is fn minus 1 plus fn minus 2. So if we calculate what should be f of x minus x times f of x minus x squared times f of x. So what should I write here? Yes.
1 minus f0 minus f2 is.
So we have f0 plus f1 minus f0 times x. Yes. And that's all. Yes. Because f1 minus f2 minus f1 minus f0 will be 0. f3 minus f2 minus f1 will be 0, and so on. So we have f0 is 0, f1 is x. So this is just x. Okay. So we find that f of x is 1 over 1 minus x squared. So we find the third expression of generation function of the f of x. And this can be helpful if we don't know the formula for the f of x, because now we can find. So I don't know if you do you know how to find the integral of such expressions? Integral. So if you have such rational function, so the quotient of two polynomials, then you can describe this as a kind of simple fractions. Two fractions. So here I can a minus x times alpha 1 plus b over x minus alpha 2. So here maybe it's better to write them into different form. 1 minus alpha 1x plus b over 1 minus alpha 2x, where alpha 1 and alpha 2 is actually the roots of some kind of roots of this polynomial. Don't need to write it in such form. Yeah, it's okay. And so you can find a and b.
The function by 1 minus alpha 1x, and then we will take f of.
Yeah, so you can write this in the following form, and then so you can find a and b from the this equality that a alpha 2 plus b alpha 1 should be 0, and a plus b should be 1. And so, but if you know this this identity, it doesn't matter what a and b is, but we know how to calculate this for all power series. So we know that 1 over 1 minus alpha 1x is just the geometric progression, infinite geometric progression. So here we have a and 1 plus alpha 1x plus alpha 2, alpha 1x squared, and so on. Yes? And this guy is b1 plus alpha 2x plus alpha 2x squared plus etc. Okay, so now we have another proof that Fibonacci numbers is sum of two geometric progressions, because from this equality I get that Fn is A alpha 1 to the power n plus B times alpha 2 to the power n. Because so this generation function is sum of two generation functions, one generation function of this sequence, and the second is generation function of the second sequence. So from this, I can have another proof that Fn is A times alpha 1 to the power n plus B times alpha 2 to the power n. And the same holds for any generation function for the sequence which can be obtained by the linear reconciliation. So if you have a sequence with which satisfies linear reconciliation, then you can do the same trick here. You can write the generation function, find the coefficients such that all of them vanished except from first two elements, and then you can write them in similar form. But of course, here will have characteristic polynomial. So this guy in the denominator is nothing but characteristic polynomial. Characteristic polynomial. Yes. This. Yeah, of course, because in last lecture we proved. Yeah.
From that one to that.
From this to this?
No.
From this to this? Yeah, because so I proved that I have following identity. So I have f0 plus f1x plus f2 squared, f2x squared plus etc. is f of x. F of x is sum of these two formal power series. Yeah, so I just look at the coefficient of n power of x. So he will have fn and he will have a times alpha 1 to the nth power plus b times alpha 2 to the nth power. Okay, but now maybe we have so we can solve linear relations using the formal power series. But now, what if we have some non-homogeneous linear reconciliations? Suppose we have now, I don't know, we have seconds an such that an is equal to an minus 1 plus an minus 2 plus, I don't know, 2 to the power n plus 3. And we have some initial values. So for example, I don't know, a0 is 5 and the 1 is 10. It doesn't matter right now. So can we find the formula for the an using generation functions? So let me start the same idea, and then we will think about how can we modify our previous solutions to find the answer in this case. So we look at the generation functions. Again, we just look at the formal power series with these coefficients. So again, we can maybe I will change it to doesn't matter. Okay, I don't know if you need to have more examples, so we can just change the coefficient here if you want. So just to look what, so we should find 2 here. Again, we can choose any number, but so for example, in this case, if we want to get them to the 0, we just want to look at the 2 times x times a of x. This will be 2a0 x plus 2a1 x squared, and so on. X squared times a of x. So here will be a0 x squared plus etc. So here we'll have an times x squared, 2an minus 1 times x to the power n, and an minus 2 times x to the power n. But now I want to have these guys also. So what should I write here? So I can just take 2 to the power n and 3. Yes, so I just take additional. So I will have 1 plus 2x plus 2 squared x squared plus etc plus 2 to the power n, and here we'll have just some constant 3. So now, if I subtract from ax all this from positives, we can just look them as. So this will be 1 over 1 minus 2x, and this is just 3 over 1 minus x. Yes? Okay. So now, if we subtract all this, we should write something like a of x times 1 minus 2x minus x squared minus 1 minus 2x minus 3 over 1 minus x is just a0 plus 4 plus a1 plus 2a0 minus 5x. So in this case, it will be 9 and 10 plus 10 minus 5, 15x. Also, if I want to, so maybe we need to simplify the equation. Here, I should write the minus. So my purchased polynomial will have good roots. Okay, so we have a simple expression, but now we have maybe a little problem, because if you want, so if you want to write this into a short way, then we need to divide this by 1 minus 2x plus x squared, and then we'll have, so we can find a of x, but the expression will be maybe not as simple as we want. So it will be like 9 plus 15x over 1 minus 2 plus x squared, but here we'll have Something like this. That, yes.
Yeah. When you multiply and a by b, the last position is
Uh,
there shouldn't be some more position.
where?
Like you multiply ax by 2,
Ax, yes. By, yes.
and the last expression, the last term of the
Here, 2 times an minus 1 times x to the power n. Yes, of course, there will be infinite sum, yes. I just didn't write it here, sorry. Yeah, of course. I should. So he will have 5, not 9. 1, not 9. Thank you. Yeah, but so here it may look hard because we have this strange guys here. But if you understand that if we, so of course again we can look at this quotient as the sum of the simple fractions, and so we can write this as a over, for example, this guy is like not a, but maybe t over one minus 2x plus dx plus e over 1 minus 2x plus x squared. And the same holds here. So here we can again write some simple fractions. So all this a of x, if we continue here, so a of x will be having will look like some to k plus lx 1 minus 2 plus x squared plus m over 1 minus 2x plus n over 1 minus x. And so we can have only 4 coefficients, and we can find them looking at the first initial numbers of sequence a of x. So I want to just show the main idea. How can we find so if we use the for all power series, we just do the straightforward calculation. We don't, so as I told you before, we can solve this by finding the particular solution. So we can find particular solution and then add any solution of the sequences, homogeneous sequences, where we can forget about this additional to the power n and 3. So we just need to find a particular solution, then we can find all the solutions. But here we can just do the straightforward calculation and have like the same answer here. So we can use formal power series just to express the linear recurrence relations. Okay. What about Catalan numbers? So I remind you that we have the following Catalan numbers. We have recurrence relation, which is Cn is equal to Cn minus 1 times C0 plus Cn minus 2 times C2 plus etc. plus C0 times Cn minus 1. And if you look at the generation functions, C of x is C0 plus C1 times x plus C2 times x squared, and so on. Then, so this formula reminds you the definition of multiplication of two formal power series. So if you take as x squared, then I will have here C0 times C0 plus C1 times C0 plus C0 times C1 times x plus C2 times C0 plus C1 times C1 plus C0 times C2 x squared, and so on. And here is just C1 plus C2x plus C3x squared, and so on. So we obtained the initial generation functions, but multiplied by no, sorry. So this is, we can obtain it if we cut the C0 from here and divide it by x. So this is, I can, so if I look like, so C0 plus x times the square root of x is C of x. Yes? Am I right? So if I multiply it by x and add C0, I will have the initial formal power series. So C0 is 1. So we have this equation, x times c squared of x minus cx minus 1 plus 1 is 0. And to solve it, I need to calculate the, so discriminant will be 1 plus 1 minus 4x. So c of x is divided by 2, 1 plus minus square root of 1 minus 4x. But so to calculate the coefficient of, if I want to find the generation function of c of x, I need to find the square root of some formal power series. So I need to find what is the coefficients of formal power series such that square of this function is 1 minus 4x. Yeah, sorry, yeah. So I need to somehow find, I need to find 1 minus 4x to the power square root this. So power will be just the 0.5 1 over 2. So I want to find if I forget about the minus 4 here, because if I find this for 1 plus x, then I can find it for, so I can just substitute minus 4 instead of plus 1, and then I will get the formula for the minus 4. So I need to find this guy. This will be just some function such that if I take the square of it, then I will get 1 plus x. We can just try to find the first. So I will give you the formula because I think you already know the formula. So if you know the Taylor series, then you will know how to write the formula for the 1 plus x to the power alpha. Yes? Yeah. And I just give you the formula, and then I will give you some kind of explanation of this formula. So of course, this is reminds you of the binomial theorem. So we already know that 1 plus x to the power n, we can just describe them into the sum of binomial coefficients. And so here I can write the same way, but so I can just write here sum from g0 to infinity. Here will be x to the power j, and here we'll have binomial coefficients of so if I have the power, so I need to write this alpha, and here will be j. Yes. What is alpha? Alpha choose j. Well, we know that binomial coefficients is n factorial over j factorial times minus n minus j factorial, but we can rule this as n minus 1 n minus j plus 1 over g factorial. And so I can generalize this formula for the arbitrary alpha and wrote it something like alpha times alpha minus 1, etc., alpha minus j plus 1 over j factorial. So this is a generalization of binomial coefficient. We can write this function for any alpha, where alpha is real for any real number. And so the question why is this formula holds? So is it true that 1 plus x to the power alpha is this form power series? What does it mean that it holds? Actually, we need only we need only one property of the formula. We need that the formula that if I take 1 plus x to the power alpha times 1 plus x to the power beta, that I will get 1 plus x to the power alpha plus beta. Yes, because if it's holds, then I can just take alpha and beta equal to 1 over 2. And so if it's holds, then it will be 1 plus x, and this is just the square root of formal power series 1 plus x. So if I want to prove this formula, so I can, how can I prove it? So first of all, I can say that something like connect this to the calculus course and say that you already know this from Taylor series, or you can just again define the so you can define the formal derivative of formal power series, prove all the properties of the derivative, such as Leibniz identity, and then use to prove that if we take the derivative on this and this, it will be correlated. And then you maybe somehow can prove this identity. So we can use the idea from calculus. Of course, if we already know this formula, the second idea is we can use this formula, find this coefficient, and just we need only to calculate this guy. So we can just try to take all the binomial coefficients of 1 over 2 over j, and then prove that this formula, this formula series squared will be 1 plus x. So we just need to check some identity straight forward check identity that 1 plus x square root of 1 plus x squared will be 1 plus x. And the second one, if we look at this formula, then we obtain some identity on the generalized binomial coefficients. So if we look, so if you want to prove this identity, we can just try prove by definition. proof by definition. So what does it mean? Just look at the. So I will write the formula. Something. So I need to prove that alpha plus beta over n is sum of from j0 to n alpha over j times beta to the n minus j. So this is the coefficient before the j's power of x in the first formal power series. This is the coefficient for x to the power n minus j in the second power series, and this is the nth coefficient in the power series in the right hand side. So I just need to prove some identity, these guys, and the idea is use something like induction here. So we just look at the, so we're trying to wrote this as the, so trying to forget about sum of alpha and beta and put them to the n minus 1. But it's just, again, will be like 20 minutes calculation, and I don't want to do it right now, so you can just think of it from how to prove it, okay? But if you want, we can discuss them in the next lecture. Because we will have some like kind of hard calculation right now, so I don't want to spend more time on calculating this guy. So if we believe that this formula holds, then we can calculate the Catalan numbers. So I will wrote okay, what should I put here? Plus or minus? What is the sign here? So let's take minus. Why? You don't know. Of course, yeah. So you know the difference between algebraic root and arithmetic root? No. Yes. So if you have, so what do you mean by square root of like 1 plus x? You have, so they have the same denotation, because so when you talk about real numbers, it is useful that all the roots, so the roots of the non-negative number will be non-negative, because you want them to be unique. It is useful to use them as a number, yes? But of course, if you take square root, you actually have two possible numbers that in square will be given this 1 plus x, yes? So if you have a real number, okay, so usually the there is a little difference between arithmetic root and algebraic root. So for example, if you have square root of 4, then arithmetic root will be 2, and algebraic root is a set of two numbers plus minus 2. And so this is correct because you just write all the roots of power 2 from 4. And here is useful because you have just number, and you know that the other root will be minus this. But why use this notation? Because, for example, in complex numbers, you don't know which of root you need to choose here. So here we just have positive numbers. But for example, in a complex plane, you have n different roots, and which of them will be the true root, I don't know. And so
Sorry.
So here, for example, I wrote just the one of the possible expression of this guy, because if you want, so if we square this guy, we will have 1 plus x. But of course, we can just take all the coefficients. If you take minus before the coefficients, then the square will be the same. And so he will.
Sorry, Professor.
Yeah.
What's the difference between arithmetic and algebraic? What do you mean by that? What do they mean?
So usually the algebraic root is all the numbers which is root of this. So
algebraic means on something like graphs.
I know maybe you have met in books another terms here, but usually algebraic root of for example of degree 2, yes. So algebraic square root of x is the set of all numbers y such that y squared is x. And arithmetic square root of x is non-negative number y such that y squared is equal to x. So usually, when you talk about real numbers, you you have arithmetic roots because we can use them as numbers just. And here is the arithmetic root. So when I take plus minus, I understand that this is arithmetic root. But okay, so I just want to how can I check? What should I take? 1 minus 4x to the power 1 over 2 minus 1 minus 4x to the power 1 of 2. We can look at the first coefficient of this formal power series and check that this will be correct. So if I want to calculate, I need to use this formula on the board to the right. So here we have sum from j0 to infinity 1 binomial coefficients of 1 over 2 over j times minus 4x to the power j. And so what is the first coefficient of this formal power series? First coefficient should be 1. Yes, so he will have 1 plus this guy will be just 1 over 2 plus 1 over 2 over 2 minus 4x squared. This is 1 over 2 times minus over 2 divided by 2 factorial, and so on. So if this should be divided by 2x, then of course the first coefficient should be cancelled. And so of course I need to take minus, because if I take I suppose you remember the formula. So if I take 1 plus minus something like so he will be minus 1 over 8 minus 1 over 8 x squared, etc., divided by 2x. Then of course I need to sorry, that will be minus. Okay. So he will have 1 over 2 times minus 4x. He will be minus 4x squared. So if I take minus, then I will have will be 0. If I take minus, so if I take plus, it will be plus 2. And this is bad because we cannot divide this over to x. But if we take minus, we will have 0 plus 2x plus 2x squared, and so on. And so we can divide this by 2x, and we'll have the 1 as first coefficient, and this is C0, so we need to take minus. But if you want to calculate the coefficients, we just need to calculate this generalized binomial coefficient. So we just want to calculate what is 1, 2 choose n of minus 4 to the power n. So let's do the calculation. Okay, so we just use the definition. We have here 1 over 2, 1 over 2 minus 1, 1 over 2 minus 2, etc. 1 over 2 minus n plus 1 minus n plus 1 over n factorial and times minus 4 to the power n. So if I try to calculate what happens inside the brackets, so in the first bracket we'll have minus 1 over 2. Second bracket will be minus 3 over 2. And the last bracket will be 1 minus 2n plus 2 over 2. So here we'll have 3 minus 2n over 2. Yes? And we have, so here we have n, the product of n elements. So I have minus 1 brackets here. So I have, so as we have minus here, I can write the minus here. And so I can forget about all the minuses. And I have 1 over 2 times 1 over 2, etc. times 2n minus 3 over 2 over n factorial times 4 to the power n. So I get rid of the minuses because all this product, all this numbers inside the brackets is negative, but we have n minus 1 negative signs. With this sign and with this n signs, we'll have positive numbers. And this is good because we should have here positive number. Okay, we can rid of the denominators because they will be cancelled with this guy. So we have just the product of the all odd numbers from 1 to 2n minus 3 over n factorial times 2 to the power n. So we of course want to add some even elements. This because we want this to be some kind of binomial coefficient, and we want to add some even numbers. So let's multiply and divide by them. So I will we divide multiply it by 2 times 4 times 2n minus 2 and divide it by 2 by 4 by 2n minus 2. So we have here in the upper side we will have 2 and 2n minus 2 factorial divided by n factorial. And we have here 2 to the power n over 2 times 4, etc. times 2n minus 2. But if we look closely, we can cancel all those. So we can divide them, all these numbers, by 2. So we have here 1, we have here 2, and here we have n minus 1. So we have here we have n minus 1 factorial and 2 in the upper hand side. So we have we will have 2n minus 2 factorial over n factorial, n minus 1 factorial times 2. Okay? Is it right? So we have here we have so sum of the guys is 2 n minus 1 factorial. So here we'll have 2, 1 over 2n minus 1, the binomial coefficients of 2n minus 1 over n. Because we can multiply and divide it by 2n minus 1, here will have binomial coefficient, and or we can write this as 1 over n of 2n minus 1, or maybe this is better. Because I just don't remember which formula of the Catalan numbers do we get in the previous lecture. Do you remember the formula for the Catalan numbers? So I think this would be better to use this formula. So if we just get out the n in the denominator, we'll get this formula. Okay. So if I need to finish, I just want to so I just calculated with this coefficient. So minus generalized binomial coefficient of 1 over 2 over n times minus 4 to the power n is this guy. And so if so c of x is 1 minus square root of 1 minus 4x over 2x. And here we have so here we'll have minus sum of 1 2 over n times minus 4x to the power n from n 1 to infinity over 2x. This is this coefficient. So this will be sum from 1 to infinity of 2 1 over n 2n minus 2 n minus 1 times x n over 2x. So 2 will be cancelled, and so we have formula of from n minus 1 to infinity 1 over n to n minus 1 choose n minus 1 times x to the n minus 1. And so if we renumerate it from the 0, we will have sum from m0 to infinity 1 over m plus 1 of 2m over m 2m choose m of x to the power m, which is exactly the Catalan number. So we proved that Catalan number is 1 over m plus 1 of 2m plus m using the formal power series technique. Okay. So This another implication of formal power series. We can use this to prove this kind of type of identities. Okay. Questions? It seems a little hard. Yes? Okay. It's okay. Okay, we will have a break if you don't have any questions. I don't know, for maybe 15 minutes. And so we have another 40 minutes. And so I think what so I don't know if you need to provide many examples here. So maybe we can just discuss some initial. So we can start, for example, partitions today, and in the next lecture we'll just say a few words more about partitions, and we'll continue to the graph theory. Or maybe you want to find about some geometry combinatorics, symmetry in combinatorics. What do you want more? What do you want more? You don't know. So I just explained on the previous lectures, and we have here we can choose one from one of two topics. One of them is partitions. Partitions is how many possible options do you have to write natural number in sum of lower numbers, sum of positive numbers. So for example, we have here 1 plus 1 plus 3, 2 plus 3, and so on. And so we want to. So there are many questions. So do we care about the order? Which type of parts can we choose, and so on? And another topic that I can talk about is some kind of symmetry in combinatorics. So it's kind of like how many different type of braces do you have? So what if we have, for example, we have cube, and we want to color all the faces of this cube in 6 different colors. So how many different cubes do we have, and so on. So we can talk about this or this. We can make a voting procedure in the Telegram. So I'll give you like 20 minutes, and you can decide it. So which of these topics will we have? But of course, we can just say about one of the topics today, and the second will be maybe on the last lecture in December if we have time. So it's I think so, because in graph theory there are infinitely many topics, different topics. So we can just stop at some point and return to combinatorics if we have time. So we can again have a discussion about what should we do in the last lecture, second topic of the combinatorics or some topics of the graph theory. So just okay. There's often situation if you need to calculate some number of combinations with some symmetry. So we start. We mainly will be discussing the necklaces or bracelets, so number of necklaces, but the same idea can be continued to count the number of different coloring of cubes, some regular polyhedron. The idea is the same. So suppose we have necklaces. So we have okay. So we have n bits, and we want to color them into, I don't know, R colors. And actually, we have two types of necklaces. So we want to. So the simple form is just that we can rotate them, and or we can rotate them and make a symmetry. So we can turn it to the other side. So the second is a little bit harder because we need to be careful about the symmetries. So we start from the simplest example. So we have necklaces, we have n bits, we can have our colors, and we want to color them and count it all distinct necklaces that we can get. We can, of course, reformulate this in terms of. So I explained it on the last lecture. So we can just say that we have words of n letters, and alphabet has r letters in this alphabet. Sorry. So we have words of length n, from alphabet consisting n letters. But we have this symmetry that if we shifted the word circularly, so we have circular shift, then we have the same word. And so I can, instead of the basic colors, I can just write the usual words. So for example, I have n equal 4 and r equal 2. So here are letters. And so I can write them into the form of, so AABB, for example, is the same as, we can shift, make the circular shift, means that we place the last letter in the beginning of the word. We have BAAB, BBAA, and BABBA, ABBA. And then will be the same. Or I can write them into just as bracelet, I can write them into the circle. So I want to count how many necklaces I have, or how many words of length n under this. So I need to say that this is, so in mathematics I can say that we factorized over the equivalence relation. So we have the equivalence relation. We say that two words are equivalent if one can be transferred to other using the circular shift. And so this is the equivalence relation. And then we factorize over it, and we counted the number of the classes of equivalence of this relation. Do you know what's the equivalence relation? You have it? Do you know? Do you know what does it mean by equivalence relation? So it's have like it was symmetry, transitive symmetry, and reflexive relation. Yes, it's called the equivalence relation, and so we have the circular shift is kind of equivalence between words. Okay, so what is the problem? The main problem is that so we, of course, we can calculate the number of the total words here, but the problem is that different types of words has different number of equivalence elements. So, for example, if you take this word, we have four equivalence elements to the element AABB. But if we take, for example, element AAAA, then we have only one element in the equivalence class, because if we shift it, it will remain the same. And so all the words are we can so we actually want to calculate not the. So in this case, we need to describe four words of so four words became one necklace, and here one word became one necklace, and we want to calculate. So what are the different types of situations can be met here, and we want to calculate them separately. And this is the main idea of how to find the formula for these words. And so actually we can have two different approaches to find the formula. And I don't know. So do you study something like group theory? No? Group theory? No. No. Yes. Yeah. So what do you know about groups? Groups? No, nothing. In algebra, abstract groups. Do you know something about them?
Yeah, we studied a little bit of permutation rotations.
Yeah. Okay. So actually here we have actually similar. So we have here rotations. Yes. So we can because I want to explain one approach today and the other maybe next spend 20-30 minutes in the next lecture. And so if you're familiar with the groups, maybe it's better to start with the group action. So for example, if we started from necklaces, then we have a rotation group. I don't know how to you don't usually denote it by Cn, but I don't know, maybe you have different and for example, in this case, we will have group the symmetry of regular polygon called Dn usually. And so we have a rotation group. So we have n different rotations. And so rotations, so we have ID, then we have rotation over alpha, over 2 alpha, over 3 alpha, and so on. Rotation on the angle n minus 1 times alpha, where alpha is 2p over n. And what I want to calculate is how can we, so how many elements of these rotations are stabilize my necklaces or circular words. So for example, I know that I have necklace and I make a rotation of this necklace. Sorry, I want to have a different colors here. So I have, for example, have some necklaces, and then I rotated it by some angle, and it became itself. So of course, if you have usual necklaces, you just rotate, and have different necklaces. But maybe there are necklaces which can be rotated and became the same. So can we say something about the angle of rotation such that it became the same? So suppose we have yeah, so we rotate just by the number of bits. So we can rotate by 1, by 2, by 3, and so on. So suppose we rotate by k bits. I don't know how. So it's by rotate by angle rk alpha, and necklace became the same. What can we say about k? So suppose k is minimal number of rotations such that this necklace became the same. What can we say about k? What? Yes, it's period. But what can we say about k? Yeah, but how it is correlated with n and r maybe? So and so for example, let's look at all the rotations that stabilize this necklace. So this necklace will became the same. What can you say? What can you say about the set of these rotations? Do you know something about this? So for example, we have like circular word, and then we know that we have like n equal, I don't know, 25, and for example, we rotate by, I don't know, 7 times, and then became itself. Can we calculate all the rotations? What is the minimal rotation of this word to become itself? No, so suppose we already know that if we rotate it by 7 bits, then its necklace became the same. What can we say about this? Yeah, so we have like A, B, C, D, E, F, G, H, and beginning A, B, C, D, and so on. So yeah, but the length is 25. Can this be obtained? Oh no. Okay, let's prove some lemmas. So let's call the period of necklace the minimal number of rotations. This to the minimal number of rotations, maybe 6 of shift. Necklace became the same. Lemma that so if there is period of necklace of length n, then so n is divisible by d. So d divided n. So for example, this can be happen that I rotated by 1, by 2, by 3, by 4, by 5, by 6, and nothing else. It became different necklaces, and on the seventh rotation, it became the same necklaces. It can be occurred only if n is divisible by 7. So why is that? So suppose we have, maybe I will start with A1. So what does it mean that D is the period of this necklace? It means that if we make a circular shift, so here we'll have one shift is an, A1, A2, an minus 1. And after the D shifts, it will be an minus D plus 1, an, A1, A2, etc., an minus D plus 1. And this should be initial word, A1, A2, etc., an minus 1. So from this, I can prove that A1 is equal to AD plus 1, A2 is equal AD plus 2, and so on. So for all I will have that AI is equal to AD plus I. Yes, because so here I have AD plus 1, AD plus 2, and so on. But if this holds, then I can write that AI is AD plus I, A2D plus I, and so on. And so if n is not divisible by n, then n is, we can divide it and have 2d plus r, where r is a residue and is strictly less than d. And so if we have n equal to q times d plus r, where r is less than d. And so if our sequences, if we shift our necklace n times, and we shifted our necklace q times d times, it became the same. And from this, we can obtain that if we shift our necklaces r times, then it also became the same. Then if we shift the necklace or rotate, so if we rotate this r times, then it becomes the same. And we can see this from here. So if we look at AI is equal to AD plus I, A2D plus I, A Q times D plus I. But the difference between, but difference between I and QD plus I, and I can write this as A I plus N. And so it means that if we shift by R, then also we'll have the same color. And so we'll find the lesser number of rotations that stabilize our necklace. And so this is contradiction to the proposition that n is not divisible by d. So for example, here, if we have, I will maybe give you an example. So suppose we have, so suppose the period of our necklace is 3. What does it mean? So if we have ABC here, then the next 3 letters should be also ABC. Then the next vector should be also ABC. So if you want to finish somehow, we need to finish on A. And to finish on A, we need to have natural number of such triplets here. And so we always the period should be should divide the length of our the length of our nexus. Okay, so I will give you the formula. So I will write the formula for the 1, 2, 3, 4, and 6. From this lemma, we can find them. And I think the arbitrary formula we obtained next time and discuss how it correlated with the group theory. So let's, because I suppose that maybe I started to talk about group theory, but maybe it's too hard to, because I need to talk about stabilizers, orbits, subgroups, and I suppose that maybe you're not, don't know what subgroup is? Yeah, okay, but what, do you know what, okay. So the main questions, what subgroups does this group have? So we have the group of rotations. Can you describe all the subgroups here? How the subgroups of this group?
Group is a subset of the elements of the group.
Yes.
The natural elements and
yes, they have natural elements, universal elements, and yes, and then the multiplication of the elements also lies in the subsets. Yes, of course. But what are the, so the simplest question is what is the subset? What is the subgroups of this group? And this can be explained that circular group. So we have like generator. So we have the generator element G, and so the all elements is just his powers. So it's group generated by G of order n. Do you know what subgroups of the, so it's just the simplest form of the group, because you just have one element and all these powers, and power is equal to E. Identity element, natural element. So what is the groups of the group? Okay, so the main idea of calculating the number of necklaces by using the group theory is just written. So yeah, it will be I will explain the main idea, then I wrote the formula for the smaller numbers, and then on the next lecture I will spend like maybe an hour to explain how this correlates. So the main idea of calculating the number of necklaces is so-called double counting, the method called double counting. So what is this table? I want to, so by the, I think the columns will be the elements of the group. So here we have E, G, G squared, G cubed, and so on. So here will be ID, rotation by alpha, rotation by 2 alpha, and so on. And by rows, I will have all different types of just linear words.
But if you have to give a subgroup.
Describe all the subgroups of this group. Okay, the answer is that all the subgroups, so this group is generated by the element G, and so all the subgroups have the same form. So all the subgroups will be having generated by the element some power of G, and so actually the same question is here. So the subgroups have the form J to the power D, J to the power 2D, etc., J to the power KD, which is N, is equal to E. So for for all divisors of n, we have the subgroup which consists of all powers of j, which is just the multiplication of d. So the powers of d. So and the idea is the same. You just take the subgroup, you take the minimal power of j, which is belonging to this group. Take all this, then all this powers will be belonging to this group, and you just prove that nothing else is held in the group, because if there will be other element, then you will have the power of g less than d. So the idea is naturally the same as here. But so when I talk about the rotations, I just try to ask you about this, but it's maybe hard. But so I just prove it straightforward using the same idea. And so by the rows, we will have all just all usual words into the alphabet of R symbols. So for example, if we have n equal 2 and n equal 4 and r equal 2, then I will write all the letters of all the words and so on. And then in the cell of the table, I will write how this element of the group, what happens if I rotate this word by this element of the group. So by ID, they all became the same, but if I rotated it by 1 alpha, it will become the so here, if you rotate from the end, it will behave like this one, this one, this one. So I fill all the table for all these words, and then I just I can count. So if I want to count the different circular words or necklaces, I just want to calculate how many. So I just want to look how many of these rows are the same. And actually, I prove that the number of these words is equal to the number of all the elements that is stabilized by the elements of the group. But okay, I just maybe it's hard to get the idea now. Maybe I'll do this in the next time in some simple examples. But now I want to give you the formula for the. Okay, formula for r equal 1, 2, 3, 4, and 6. Okay, so if we have one letter, then we have nothing to do. We just take. So let me denote by n of, and maybe the wrong word, but necklaces. Okay, well, let's take it's the number of necklaces. Okay, so n of n1. So if we have only one color, we have only one necklace for each color. So we have, oh, maybe I want to take n equal to 1. Sorry. So I want to have constant number of bits and different number of colors. So sorry. So for n of 1 and r, we have exactly r different necklaces, because I can just have no options. Yeah, I have just no. So sorry. No, it was correct. Sorry. So here I have only one color. So the answer is just 1, because I have only one option. Yeah, sorry. Maybe. No. So, and sorry, let me think what I want to count, what I want to calculate. No, sorry. Yeah, so let's talk with, yeah, it was okay, yeah. So again. For 1 and R, we have exactly R necklaces. So, for example, if we have 3 different colors, we have 0, green, red, and blue necklace. And if I have, let's calculate n 2 of R. So suppose we have 2 bits. As you know, we have for each necklace, the period should be 1 or 2. So either we have the bit that, so this bit of period 1, and if we have different colors, that it means that we have the period of this necklace will be 2. Okay, so what are the necklaces of period 1? If we look them at the words and just look at the usual words, it means that they consist only of 1 letter. Yes? So we have exactly our elements of period 1. And for them, we will have exactly our necklaces. Period 1. Okay, so how many other words of period 2? So we have like AB and BA. Yeah, but if we have our elements in the alphabet, our letters in the alphabet. So we should consist. So the total number of words of length 2 is R squared, and we already count the R of them. So the number of these words will be R squared minus R. Yes, because the total number of words consisting to letter is R squared, and the number of words with the same letter is R. And so for these guys, from each 2 words, we have 1 necklace. So here I should write something like R squared minus R over 2. This is the number of necklaces of period 2.
Why?
Because from these 2 words is 1 necklace. So I take, if I wrote the colors, I can take green, red, or red, green, and this is the same necklace. Okay, so if the length is 3, then of course, so the period of these necklaces should be the divisor of 3. So either we have period 1, or we can have, period 3. And again, we have R of period 1 and R cubed minus R over 3 of period 3. Because we have R cubed total words, we subtract all the words of period 1, and from 3 such words, we have only 1 necklace, only 1 circular word. Okay, so the total number of words consisting of 3 letters is R cubed. Okay, so for example, we have letters A, B, C, and D. we have four words that consist of only one letter, and all other words are divided by pairs here. So how many total words do we have here? We just calculate the total number of words, which is 16 of two letters, and subtract 4. So the total number of words is 16 minus 4, 12. And each two words is one circular word, or one necklace. So we need to divide it 12 over 2. So we write it's here. And the same goes for N3R. But then it became a little bit complicated because, for example, for N4R, we have three types of periods. Periods 1, period 2, and period 4. And so period 1 will be the same. Period 2 will be period 2. Actually, it will be the same, but I need to explain this. So period 1 will be the word consisting only of one letter. What does it mean that word had period 2? It means that we have the same word repeating 2 times, and the word it has exactly two different. So we have two linear words from one circular word. Yeah, so it will be the same, r squared minus r over 2. Because we just need to know about the first two elements of the sequence because the other will be the same. And these two elements can be of two types. And now we need to calculate the period 4. So we need to take all elements, which is, minus what we counted before, and divided them over 4. So what we count? We counted exactly r words here and r squared words here, minus r. So actually will be r to the power 4 minus r over 4 here, minus r squared over here. So we just subtract this one and this one. And this becomes more complicated if we add. So if the number n has many dividers, then this formula became more complicated. For example, if we have n of 6r, it will became something like r plus r2 squared over 2 plus r cubed minus r over 3 plus r6 minus r cubed minus r2 plus r over 6. So you maybe can do this at home, check that like this formula is correct. Because we need to take all linear words, usual words, and then subtract what we counted before. This will become r squared because this is like r first minus r squared plus r minus. Sorry? Because here we counted only linear, only usual words. We don't count the circular words. We counted how much of linear words. So we have 4 places. Each of these places can be chosen from our alphabet elements. And so we have total r to the 4th power words, but we already counted r here and r squared minus r here. Yeah, okay. So the question is, what should be here for arbitrary n? and I will answer the question in the next lecture and connect this. So I will take I will explain this formula and then explain it in the terms of group theory. Maybe I will write the picture for the smaller r and show you how the group theory can be used here to calculate the number of necklaces and generalize it to any type of symmetries of then you can have